Welcome to this set of tutorials about the auditory system. We'll begin with this session speaking about peripheral mechanisms that are important for transferring the energy in the environment in the form of sound waves into electrical signals that will be processed by the brain. These topics will relate to several of our core concepts in the field of neuroscience. We'll be speaking of the complexity of the brain. We will introduce a new core concept with this session, and that is that the brain makes it possible to communicate knowledge through language. So while this session is not explicitly about language, certainly any discussion of the auditory system would not be complete without at least some mention of human speech. And, well, of course, it's our brain that brings us here this evening and endows us with a natural curiosity to understand how the world works. I have two learning objectives for us this evening. First, I'd like for you to be able to describe the biomechanics of sensory transduction in the middle and inner ear, including the important concept of tonotopy that is established in the basilar membrane. I want you to be able to characterize the neurophysiology of sensory transduction in auditory and vestibular hair cells. Now, our focus is on the auditory system, but as you'll see, the very same mechanisms apply to the sensory transduction apparatus of the hair cells in the vestibular system, which will be a topic for a tutorial that we will come to very shortly. Well, I want to begin with providing you an overview of the auditory system and auditory function. And we're just going to step right through this. If you don't want to read as I'm talking, then just listen. But otherwise, I want to put the words in front of you because these next two slides really provide a bulleted framework for our discussion of the auditory system. Well, let me begin by just stating for you what is the challenge in auditory function. Well, the challenge really is to transduce energy that comes in the form of sound waves. Well, this is what the auditory system does. It transduces sound waves into distinct patterns of neural activity that are then integrated with other sensations and motivations to guide behavior. So, once again, in a sensory system, we need to consider the process that begins with sensory transduction and ends with the guidance of behavior. Now let's see how the auditory system accomplishes these goals. First of all, sound waves are collected and amplified by the physical structures that comprise the external ear and the middle ear. And these structures transfer that energy to neural elements that are present in the inner part of the ear. The biomechanical properties of the inner ear then decompose complex sounds, such as the sound of my own voice, into sinusoidal components, so that the component frequencies, their amplitude, and their phase can then be encoded in the firing of the receptor cells. What comes next is the establishment of a principal form of mapping that we see in the auditory system, which is called tonotopy, or the mapping of auditory tone. So in the inner ear, and then throughout the rest of our central processing stations, tonotopy is preserved. The story continues in the brainstem. What we see is that auditory information is first processed and divided into several parallel pathways in the brainstem. Some of these pathways will compare the signals derived from the two ears, and this allows for the localization of sound in auditory space. Within the brainstem, there are centers that relay information up to the midbrain, and there an important integrative center is the inferior colliculus. So the inferior colliculus of the midbrain, in turn, sends projections to the auditory division of the thalamus, a region called the medial geniculate complex. And then, as we've seen in our other sensory systems, the specific thalamic division that receives this ascending sensory information projects to the cerebral cortex. and therefore defines what we will call the primary auditory cortex. So within the auditory cortex, information is received from the thalamus, and of course it's further processed and further elaborated, and the more complex aspects of sound are represented, including the sounds of human speech. With that broad overview of the functions of the auditory system behind us, now let's consider each step along the way, beginning with the nature of sound. Well, sound comes from spherical pressure waves of vibrating air molecules, and one simple way to induce such vibrations is with a tuning fork. Well, I happen to have a tuning fork with me here, and if I just tap it appropriately, I can hear the vibrations of the tines at a frequency of 440 cycles per second, or 440 hertz. Perhaps you can hear that as well. Of course, another way to produce that kind of a tone would be with a musical instrument. So I happen to have my guitar with me, and here's the tone that I just produced by the tuning fork. Well, of course, if my guitar is in tune, that is. That should be very close to the frequency of 440 hertz. Here's another tone, which I'm particularly fond of for some reason. That is the tone of an F sharp, which is just below 440 hertz. As I've set in motion the tines of the tuning fork or the string of my guitar, what I've done is created spherical pressure waves. And these pressure waves can be characterized really in terms of three fundamental properties. The amplitude, which has to do with the depth of this modulation, of the contraction and expansion of these pressure waves as they travel through air. So amplitude is what we interpret as the intensity of the sound. Another parameter has to do with the pitch or the frequency of the wave. That is, what is the distance between one peak and another, or one trough and another? So the frequency is what we interpret as the pitch of that tone. And as sound is perceived by the two ears which sit on either side of my head, another aspect of this spherical pressure wave that's traveling through space becomes important. If we imagine sound coming from one side of our location or another, then there will be a temporal shift or a phase difference between the waveform that's encoded in one ear compared to the other. So a difference in phase becomes an important property of sound as we perceive it in our two ears that becomes encoded in the firing patterns of auditory nerve cells. Now, sounds in the environment and the sounds that we ourselves produce in speech were simply single frequencies of sound that could be characterized by a simple sine wave. Well, perhaps the job of auditory processing would be quite simple. But then again, perhaps life would be a little less interesting. Now, this F sharp by itself makes a rather pleasant tone, but I'm rather fond of it in the context of a chord that is more complex and includes other tones. And even human speech is incredibly complex. It seems like it might be a rather simple auditory stimulus, but there are all kinds of frequencies with varying pitch and varying phases depending upon how these different temporal frequencies are combined as we make different speech sounds. So human speech presents a great example, just as appreciating a complex pattern of tones in music presents a great example of the challenge faced by the auditory system. So now let's talk about how this energy in the environment actually is collected and then transduced by the structures of the ear and ultimately converted into electrical signals that travel into the brainstem. So just a quick bit of anatomy of the human ear. So we see a very nice illustration here of the anatomy of the external, the middle, and then the inner portions of the human ear. And the external ear looks a little bit odd, odd in some of us more so than others, but its structure has a particular purpose. What this external ear is doing is it's collecting sound frequencies from our environment. And the shape of this external ear, including the pinna and the concha, is acting to collect those frequencies that are particularly germane to our environment and especially to the sounds that we ourselves produce. So our external ear gathers sound and allows that sound then to be focused and concentrated as the sound pressure waves enter the external auditory meatus on their way to the tympanic membrane, which we find on the medial edge of the external auditory meatus. These structures also filter sounds and are very useful in helping us localize sounds in the environment. We become attuned to those sounds that are specifically filtered and funneled down into this external auditory meatus. Next, let's turn our attention to what we find in the middle region of the ear. So if we look more closely at this region, what we find is the tympanic membrane, which is a diaphragm that sits at the junction of the external and the middle ear. And just on the medial side of the tympanic membrane, we find three of the most exquisite bones of the human body that one can discover. These are called ossicles, the ossicles of the middle ear. They are the malleus, the incus, and the stapes. And they articulate in a particular way to achieve a biomechanical leverage over the sound energy that's being transmitted from the vibrations of the tympanic membrane. In fact, there's about a 200-fold amplification of energy from the impact of that sound energy on the tympanic membrane to the piston-like action of the stapes pressing against the inner ear. The stapes makes contact with a region that we call the oval window, and it vibrates in and out. And again, about a 200-fold amplification of energy occurs through the way the biomechanics of these ossicles align and transmit their energy as they articulate. And next, let's have a look at the inner ear. The inner component of the ear is comprised of a beautiful set of membranous canals that run through the petrous temporal bone. There are essentially two divisions of this structure. There's an auditory division, which is found here, and it's represented by a snail shell-like structure called the cochlea. And there is a vestibular division, which we'll come to in a subsequent tutorial, that includes a set of sensory structures that are sensitive to the movements of the head. So for sound, the cochlea is the structure of interest. This cochlea really has a twofold purpose. It has a biomechanical function and a neural function. The biomechanical function is to decompose complex sounds into their component frequencies. The neural function then is to transduce this mechanical energy into neural signals that are then communicated through the auditory nerve and into the brainstem. Now let's look more closely at the anatomy of the cochlea. So cochlea is a Greek word that means snail, and it refers to this coiling that we see resembling the shell of a snail. And if we were to look at a cross-section through that cochlea, what we would see is a set of membranous channels. In fact, we see two large channels that appear to be bisected right through the middle. And if we look carefully at that structure of bisection, we see yet a third channel. So here's an enlarged view over to the right, and what we find are these large fluid-filled channels. And this partition that separates those two large channels has buried within it a smaller channel and a set of exquisite structures that are present on the base of this partition. So just a bit of nomenclature here. So the coiled structure that we find is called the cochlea, and the partition that we see is called the cochlear partition. And then the base of this cochlear partition is a structure that we call the basilar membrane. The basilar membrane has a roof. You may remember from the neuroanatomy of the midbrain that another word for roof in brain anatomy is tectum. So there is a roof over this structure called the tectorial membrane. So there's a basilar membrane below and a tectorial membrane above. And making contact between the basilar membrane and the tectorium are the sensory cells. And these sensory cells are called hair cells. From the apical surface of these hair cells are cilia, and these cilia make contact with the tectorial membrane that forms the roof over this epithelium that sits on the basilar membrane. The cochlear partition is innervated by the peripheral processes of nerve cells that sit in a ganglion that spirals around the turns of the cochlea. So this ganglion is called the spiral ganglion, and it's the ganglion, or it's the location of the cell bodies that grow the auditory component of the eighth nerve. The peripheral components of these spiral ganglion cells grow out and make contact with the basal region of the inner hair cells. We also find an additional collection of hair cells called outer hair cells. And these outer hair cells really are not sensory cells at all. Rather, they serve an important biomechanical function where they actively tune the vibrations of this structure as the basilar membrane articulates with the tectorial membrane. And then lastly, I'll highlight this inner channel that runs through this cochlear partition. It's called the scala media, and it contains a very different kind of fluid than what's found in these other larger spaces, the scala vestibuli and the scala tympani. And as we'll see, the fluid in the scala media is critical for the process of sensory transduction in the inner hair cells. One more point to make about these channels that run through the cochlea. As the spirals of the cochlea reach the apex, the scala vestibuli and the scala tympani actually come together around the tip of the basilar membrane, right here at the apex of the cochlea. So there's actually continuity in the fluids that are present in these two large channels that run the length of the cochlea.